Good day and welcome back to part 2 of our discussion of triple integrals and spherical coordinates. In our previous video we introduced the spherical coordinate system and we saw that spherical coordinates are well suited for describing both spheres and cones. In fact, remember their equations are about as simple as they can possibly be. A sphere of radius c centered at the origin is represented as rho equals c, and cones are represented by phi equals a constant. Furthermore, let me remind you of the standard relationships between Cartesian and spherical coordinates. So we have x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. Our goal in this video is to discuss how we can evaluate a triple integral in spherical coordinates. What I have pictured is a solid of integration E, which we are going to think of as a spherical wedge. We're going to have the rho, theta, and phi values all bounded between constants. And let's see if we can indicate where all of those quantities would lie in our picture. So to begin, note that we have this upper portion of the wedge, and we're thinking of this as being rho equals b. We're further away from the origin. And in order to indicate the bottom portion, let's get some dashed lines here to represent kind of depth. In yellow, we would have rho equals a. So the side of this spherical wedge closer to the origin. Then our theta values between alpha and beta would be if we were to project our surface down into the xy plane, then alpha and beta is measuring kind of those standard polar type coordinates we've encountered before. And then remember the phi value measures a similar thing, but it's an angle coming down from the positive z-axis. So we can see our phi values as being phi equals c, the smaller angle, and then phi equals d for the larger angle. And it's also worth noting our standard restrictions. We think of rho, since it measures a distance from the origin, as being a non-negative quantity. The theta value can range from 0 to 2 pi, as it always has, and the phi value can range from 0 to pi, and that's simply to make sure that we're not counting or representing a point in two different ways. So now for the new part. If we have this spherical wedge, something convenient to describe in spherical coordinates, how do we set up that triple integral? And the idea is that we take our spherical coordinates and we rewrite every x, y, and z accordingly. So we have f of rho sine phi cosine theta, then y becomes rho sine phi sine theta, and z becomes rho cosine phi. And note, this is the most abstract possible perspective. In a moment, we will investigate a nice concrete example. Furthermore, though, the dv needs to be written in terms of spherical coordinates as well. So there's going to be a d rho, d theta, d phi, and similar to the r, with the r, dr, d theta with polar coordinates or cylindrical coordinates, we need to add something additional. And that additional thing that we need to add is rho squared sine of phi. So note, this entire quantity at the end is representing our dv. And at this point, it is in no way clear or obvious at all where that rho squared sine phi comes from, but I'll note that this is something that we will encounter in our next section, and we'll have an idea of where that's coming from. For now, I'm going to simply write it down and use this formula. We also need limits of integration, and since our limits of integration are all between constants, The order is once again kind of irrelevant, as it has been previously, as long as we align things appropriately. So we have rho on the inside, which varies from A to B. We have theta in the middle, varying from alpha to beta, and phi on the outside from C to D. And just to recap the takeaways, we need to convert each Cartesian coordinate in terms of spherical coordinates. So we're going back to those equations that we have previously introduced. So x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. And then lastly, we need to rewrite the dv. And as we've seen, dv is going to be rho squared sine phi times d rho d theta d phi. And we'll now investigate several triple integrals in spherical coordinates. In this first very common type of example, we are asked to evaluate a triple integral over some solid which is described. And note the solid lies between a sphere of radius 1, centered at the origin, and a sphere of radius 2, centered at the origin, specifically in the first octant. So thinking about this relative to spherical coordinates, this is the ideal scenario. Rho equals 1 and rho equals 2. This should be a solid of integration where spherical coordinates would apply very nicely. And let's go ahead and sketch what our solid will look like. It's bounded between a sphere of radius 2 and a sphere of radius 1 in the first octant. And remember, our pictures do not need to be perfect, far from it, just get that general idea across. So we have a sphere of radius 2 in blue, and then we have a sphere of radius 1 in red. And it's everything between these two. So think of it as a portion of this sphere of radius 2 where we've hollowed out the inside. To convert this triple integral into spherical coordinates, it's ideal if we can describe what I'm going to think of now as a spherical wedge in spherical coordinates. That is, from our above picture, how do the rho values, the theta values, and the phi values vary? And let's just kind of talk our way through this intuitively. We're between the sphere of radius 1 and 2. So our rho values can be as small as 1 and as big as 2. We are restricted to being in this first octant. And remember that if you look at the positive x-axis, that would correspond to theta equals 0. The positive y-axis would correspond to theta equals pi over 2. And our theta values are going from 0 to pi over 2. And a nice thing to note is that the theta value that we used in polar coordinates is the same theta value we use in cylindrical coordinates and the same theta value that we use in spherical coordinates. The phi is a bit different. It measures this angle coming down from the positive z-axis. You can be phi equals 0 and you can rotate all the way down to that xy plane, which would be phi equals pi over 2. And once a solid is described in spherical coordinates, we can hopefully quickly and efficiently evaluate or at least convert this triple integral. So the triple integral over this solid E of z dv. So note, we first convert everything in our integrand into spherical coordinates. And z is equal to rho cosine phi. dv is rho squared sine phi, d rho d theta d phi. And because our limits of integration all are going to vary between constants, we can actually order these limits in whichever way is most convenient. I have rho on the inside from 1 to 2, and then theta and phi are both 0 to pi over 2. And getting it to this point is really what I think of as kind of the new part of this problem. This is a triple integral that we can evaluate using our standard techniques of integration. And one thing I would even note is that we have a function of rho cubed, times a function of phi, and our limits of integration are all numbers. So we could actually immediately split this up into three single integrals multiplied together. We have an integral in terms of phi, an integral in terms of rho, and lastly an integral in terms of theta. And each of these three integrals are extremely reasonable to evaluate. The second two we can do almost immediately, while the first one would be aided by a substitution. So maybe you would want to do something like, say, u equals sine of phi. And at this point, I will let you work through the details, but once you have done so, and note my optimism, what you should end up with is 15/16 pi. Let's move on to the second example. Let's set up a triple integral to find the volume of the solid, which is enclosed inside x squared plus y squared plus z squared equals 2, above z equals 0, and below the surface z equals the square root of x squared plus y squared. And let me start off with the intuition. Because we have a sphere and a cone, it seems reasonable for us to try spherical coordinates. And because students typically ask, it's also worth mentioning that when we have the equation of a sphere, sometimes we can make it work in cylindrical coordinates, but that's not always the case. So let's first represent these two surfaces in terms of spherical coordinates. We have a sphere of radius square root 2, so be careful, rho equals root 2. And we also have this standard cone, so phi equals pi over 4. And before setting up the integral, let's go ahead and sketch the solid of integration whose volume we are going to find. And it's worth reminding you that when it comes time to, say, exams, I will have a portion of the question that asks you specifically to sketch the solid. So this is something that we have to make sure we are practicing. So for this solid, we are inside a sphere of radius square root 2, so just kind of a generic sphere, above the xy plane and below the cone. And let's now go ahead and get rid of a few extraneous lines. So we are below the cone and inside this sphere of radius square root 2. And hopefully this gives you a picture of what this would look like. It's a hemisphere, so the top half of a sphere, and we've hollowed out this conical shape so that the solid that remains is underneath that hollowed out cone shape. And note that this is something that we can very conveniently, once again, describe in terms of spherical coordinates. And I would like you to pause the video and take maybe 2 or so minutes and describe this solid in spherical coordinates, that is, add in these restrictions, and then set up that triple integral in spherical coordinates that represents its volume. Now that you've paused the video and thought about this for a few minutes, note that in this solid, the rho value varies from 0 to square root 2. We rotate all the way around the z-axis, so theta is from 0 to 2 pi. And we are going from this standard cone given from phi equals pi over 4 down to where we hit the xy plane, which is phi equals pi over 2. So our phi values are ranging from pi over 4 to pi over 2. And that's the key part of the problem. So the volume of this solid E is the triple integral over E of 1. When we convert this to spherical coordinates, the dv, recall, is rho squared sine phi, which gives us an integrand. And then we have d rho, d theta, d phi. And once again, because our rho, thetas, and phi's vary between constants, this order is going to be irrelevant. So rho on the inside is from 0 to root 2. Theta in the middle is from 0 to 2 pi. And phi on the outside is from pi over 4 to pi over 2. Which answers a question that has been asked. We've set up a triple integral representing the volume of this solid. Note the previous two examples have been very common standard types of examples we might encounter. And in both of them, the rho, theta, and phi, those variables in spherical coordinates, have varied between constants. When that occurs, we can order our variables of integration in whichever order is convenient. But I'll throw out there just the caution, this will not always be the case. And we will investigate such an example in our next video. So stay tuned and take care.